So first of all, thank you for accepting to give this webinar, Michel. So Michel is one of our worldwide experts of mass measurements and laser spectroscopy, especially in the mass region of heavy nuclei. So after his PhD in the University of Mainz, he started a postdoc in 2002 at GSI on the ship trap project. Then he spent 1 year at NSCL before he got a permanent position at GSI in 2007, and as a staff scientist. And then since 2015, he's professor at the Department of Chemistry at the University of Mainz. And since recently, since last July, he's also the director of the Helmholtz Institute at the University of Mainz. I also would like to say that he was awarded of the Flare-Off Prize in 2013. And today you will talk about laser spectroscopy in exotic nuclei. So thank you again, Michel, and you can start when you want.
Yeah, thank you very much for the nice introduction and also for inviting me to give this presentation. It's a great pleasure to do so. Yeah, then I will start. So I was asked to talk a little bit on how one can obtain certain properties of exotic nuclei from laser spectroscopy. And I will really start with a few very basic considerations, as this is a relatively broad audience. So my idea is to give you a few basic concepts. What type of nuclear properties can we obtain from laser spectroscopy and how do we do it? I will introduce you very briefly to two of the very most common methods, which is collinear laser spectroscopy and resonance ionization laser spectroscopy. And then I will show you a few select results from different experiments around the world. It will depend on how much time I have used up, what I will be able to show you. That is the plan for the moment. All right, so I mean, I guess all of you know that the atomic properties and structure is connected to the emission of light. So if you here see the emitted light from different elements, you of course see distinct lines, and you also see that these ones are all different. I apologize that my labels somehow got missing. So we are starting from hydrogen over helium to mercury to uranium. And of course, if you compare the hydrogen spectrum to the uranium one, you can see it looks quite different. So there is a lot of information hidden in these lines, their intensity and their position. And this we can, of course, use on the one hand side to really learn something about the atomic structure. So which kind of electronic states are there, what are their energies and lifetimes, and so on and so forth. But we can also at the same time use an electron in the atomic orbit to probe the charge distribution of the nucleus and let it interact via its spin, for example, and then obtain magnetic moments, quadrupole moments, and so on. The hyperfine structure splitting by itself and the isotope shift will provide us access to nuclear shape and deformation. So this is the key idea here, using the electrode as a probe to the nucleus. Now, how do we do this? So, well, of course, if we have a spectral line, then we will record a certain number of counts at the different frequency positions. And such a line is observed in different isotopes that, for example, have different numbers of neutrons, then it will shift in the transition frequency. And I will show you in a moment how this is connected to the changes in the mean square charge radius. And then the hyperfine structure splitting will give us access to dipole and quadrupole moments, but also this I will elaborate a little bit more closely. So let's first look into the isotope shift. So what we have here is a shift in a transition on the ppm level. And if you would go to this cartoon picture of a nucleus with a certain size, you can see the green and the red one, they differ a little bit in size. And of course, this changes the shape of the nuclear potential, and accordingly, the energy levels will shift. As I said, this is a small effect, ppm, but since we can measure the atomic transition frequencies to a very high precision, we are sensitive to observing these so-called isotope shifts. If you parameterize these isotope shifts, so this is the difference in the transition frequency between an isotope with mass number A and A prime, and then there's basically two factors. One factor is called the mass shift, where part of it is the change in the reduced mass. I mean, if you remember how you derive the atomic energy levels of a hydrogen atom, at some point you make a separation between the center of mass motion and its relative motion. So this is part of what goes in the first factor. And then the second factor is what we call the field shift. And in the field shift, we have an information on the change in the nuclear charge distribution or the nuclear volume. And of course, in principle, you can make some sort of an expansion. For most practical cases, only this first term, delta R squared, will be of relevance. I should mention that when we talk about exotic nuclei, and I hope that I will give you a few examples from the very heavy elements, then sometimes we have cases when we do, for example, in the heaviest elements, not have stable isotopes. And if we do not have stable isotopes, we often will need atomic theory to obtain this F factor for the field shift, or even the M factor from atomic theory to have a reference point. I mean, what we can always do, of course, we can make relative measurements of isotope A to A prime if we have some data for isotope A. But of course, if we would like to know even absolute numbers, we need definitely a reference point. So this is something we should keep in mind. The other point that I wanted to mention briefly, if you look into these different parts, the mass shift and the field shift, in this case plotted as a function of the atomic number, you see that one goes up and one goes down. I mean, the field shift from the nuclear point of view is usually the one that contains the information on the nuclear structure. And so this is indeed the one that we normally want to obtain. So in principle, the life gets a little easier if we go to heavy elements, because this becomes the dominant contribution. If you study very light elements, I mean, for example, several years ago, there were nice studies on lithium, then you really have to measure very precisely, because this mass shift is very large. But this is more or less something we can in principle get under control. The changes in the mean square charge radius contain information on the charge distribution and thus on the nuclear shape and the deformation. And we can compare it, of course, with the different theoretical models. And so you can make a comparison and say, okay, the delta R squared that you obtain from your measurement can be parameterized. I mean, this is only one of many possible ways, but you can say, okay, maybe there's the part of a spherical contribution, and then you can add, for example, a quadrupolar deformation or higher order terms, depending on what you would need. So the main point is we can have an information on the nuclear size and shape and connect it to the measured properties from the frequency shift in two different isotopes. The other basic information about the nucleus we can obtain from the nuclear hyperfine splitting. So here you see an example, an atomic ground state with an angular momentum of 0, an excited state with an angular momentum of 1, and a nuclear spin of 5/2 would result in a hyperfine splitting of the upper level. And the hyperfine splitting is, of course, leading to a coupling of the nuclear spin and the atom's angular momentum to a total angular momentum of F. And this different F quantum numbers, 3/2, 5/2, and 7/2, are given here. And you would, from the ground state in my example, get 3 different transitions. And from these transitions, from the position of the transition and from the relative intensities of such a pattern, you can, of course, obtain various information. I mean, here you see the energy splitting delta W is given by these numbers here, these constants, which are mainly related to the spins I, J, and F. And yeah, of course, as I said, from the splitting pattern and the relative intensity, provided you have sufficient statistics, you can really distinguish which nuclear spin gives you a correct fit of your spectrum. And of course, you can also obtain a magnetic dipole moment or a spectroscopic quadrupole moment. And this is connected to these two factors A and B in the splitting pattern. So the factor A is connected to the nuclear dipole moment, a magnetic dipole moment, depends on I and J, and BE of 0, this would be the magnetic field that the electrons produce at the location of the nucleus. The B factor is connected to the spectroscopic quadrupole moment QS, and delta V over these deltas, I mean d to V to dc squared, this is the gradient of the electrons at the position of the nucleus. So these properties A and B you can obtain from a fit to a measured hyperfine spectrum, and then you can have information on these electromagnetic moments of the nucleus. So these would be the parameters you can extract from optical or laser spectroscopy. Now, of course, there's a few things that you have to consider. Let me start first by some technicalities. I mean, if you have an atomic transition, then of course you will get a certain spectral response function. So this would be the number of photons in a normalized way as a function of frequency. The natural line width delta nu would be, of course, according to the uncertainty principle, related to the lifetime of the excited state that you would look at, and that would usually give you this green curve, which would be of a Lorentzian shape. Now, if you think about typical cases, if you have an allowed electric dipole transition and a typical atomic state where you have half-lives, lifetimes on the order of a few nanoseconds, say 10 nanosecond order of magnitude, then the half width or line width that you would obtain is on the order of tens of megahertz approximately. Now, if you take a commercial pulsed laser system with a few, let's say, frequency selective elements, you would probably end up at a line width on the order of 1 to 3 gigahertz. So if you had such a laser system, you would already, from the resolution of your device, not be able to resolve the spectral line width of your transition. If you had a CW laser, of course, you can have line widths well below 100 megahertz. I mean, if people make really sophisticated laser systems, for example, in optical clocks, you can have, of course, a laser stabilized to even 1 hertz or maybe sometimes less nowadays. So you can have very narrow band lasers, but at the same time, you need a certain intensity to obtain saturation. Now, there are several broadening mechanisms in a practical experiment that also limit your resolution. And of course, one most commonly is the so-called Doppler broadening, which is related to the temperature of your atoms. And this would normally lead to a Gaussian line shape and is very relevant if you have, for example, a hot cavity ion source where you naturally evaporate atoms at high temperature. The Doppler broadening can be compensated if you have a cooling mechanism, or if you have a trick to maybe somehow reduce the energy spread, as I will explain you in a moment. Then, of course, if you are working in a gas environment, I mean, I will show you some examples from measurements that have to be done in a gas cell, then you might have a pressure broadening due to the collisions between the atoms that you want to study and the background gas or buffer gas atoms that you have. And very often this will lead to this blue type of shape, which is a Voigt profile, which is sort of a folded line shape between a Gaussian broadening and a Lorentzian curve. And this is what you often look at. And then you can have additional power broadening if you use a high power laser, which would oversaturate your transition. Then it could also lead to a broadening mechanism. So this would be some things that could limit your resolution. And I mean, the resolution that you require depends on what you want to measure. But as I said before, if you, for example, want to measure a full hyperfine spectrum where you need the relative intensities, you probably need high resolution. Now, there is another point that is important, and this is related to the detection. Now, if you think about the most basic case, you have some atomic ground state and some excited state. You can, of course, take tunable laser radiation and do an excitation. And then after a certain lifetime, you will have the fluorescence by the de-excitation back to the ground state. As I have said, we typically are talking about, for electric dipole transitions, half-lives on the order, lifetimes on the order of nanoseconds. So if we would like to make an estimate, what does it mean in the number of photons? Well, of course, yeah, this is approximately proportional to 1/tau. So we would, from a 10 nanosecond lifetime level, get about 10 to 8 photons per second, which is quite a reasonably high number. However, if we really detect the fluorescence light, say by a photomultiplier, then we usually have a limitation, first of all, by the detection efficiency. This is normally not so much of a problem, but the solid angle coverage can indeed be a problem. I mean, just for practical reasons, you don't always get the detector as close to the atoms that you would like. And so very often typical overall efficiencies of optical detection systems can be as low as 10 to -3 to 10 to -4, which would still correspond to about 10,000 photons per atom. This is in principle, if you have a low background environment, sufficient to make an image of a single atom. However, in practical environments, you often have various sources of background. And one of the background sources can, of course, be scattered light by the laser, because if you look at the simple example that I sketched here, you would observe fluorescence on the same transition where you do the excitation. However, your laser photon rate might be much higher than the rate you can collect from your fluorescence in the spontaneous emission. So the challenges that you normally deal with is a background from scattered laser light. Other issues are you need suitable transitions. I mean, where suitable means on the one hand side, you would like to have strong transitions to have a good excitation probability, but suitable also means you have to have a transition where tunable laser light of a good quality is available. The other issues, as you will see in many cases, we will have to work on neutral atoms. I mean, this might not sound like something important, but in practical terms, it can happen that sometimes we would rather have an easier time to start from ionic systems, but then the transitions may be in unfavorable regions. Yeah, so mostly it is then the wavelengths would be more in the ultraviolet, where at present we still have limited availability of laser systems. So this problem can be circumvented. And one way of doing so is, I mean, let me first go to the fluorescence detection maybe before we go to the next version. So for fluorescence detection, there's various ways. I have just picked one example, which is very frequently used. That is the so-called Collinear laser spectroscopy. This has been pioneered in the mid to late 1970s, mainly in the group of Ernst Otten, at that time still in Heidelberg, shortly after in Mainz. And it came to application online first at ISOLDE. The idea is you have an ion beam that you accelerate to an energy of, let's say, 30 to 60 keV. And this you do because your ion beam, when you create it inside your ion source, will have an energy spread delta E. Now, if you look into the velocity spread, then this velocity spread can be compressed if you accelerate your particle to an energy E, which is proportional to the charge times the acceleration voltage U. So that means you have an actual compression of the velocity spread in such a configuration. So what you do is you accelerate your ion beam to this moderately high energy by a certain set of electrodes. And then you have a transition frequency, which is due to the Doppler transformation change. So nu zero would be the transition frequency in the rest frame of the atom of interest. And then you see here, these are the Lorentz parameters, beta, which is V over C. And this is the corresponding gamma parameter. Now, this has a few implications. First of all, you have the possibility to change your transition frequency. So C stands for collinear and A for anti-collinear. So this will just explain you these different signs here. But the practical consequence, besides the compression of the energy spread, this is important because this allows you to come close to the natural line width. But at the same time, you have a chance to use a fixed frequency laser beam and overlap it with your ion beam. And then you can use a change in the ion acceleration voltage to achieve a frequency detuning. Since you start with an ion beam, you will usually do a charge exchange, which you can do with a vapor, for example. Sodium vapors can be used or something like this. and then you can do a resonant charge exchange, and then you have neutral atoms in the same direction as your initial ion beam, and then you can perform a laser interaction by overlapping your laser beam, and then you have a fluorescence detection region. So we do neutralization by charge exchange, as I was saying. We can do excitation in collinear or anti-collinear geometry, and typically we observe fluorescence. I mean, there are some cases when also radioactive decay is involved. For example, some experiments have been done studying benefiting from a better symmetry, but I will not discuss this in more detail at the present stage. Yeah, as I said, you have a detection here, so you have a limited time for which the atoms can emit their photons. And I mean, as I mentioned before, we have a laser related background. So a couple of years ago, a trick was introduced benefiting from new technology that then had emerged. And this is using a so-called radio frequency Cooler buncher. This is a device in which particles can be confined by RF and DC fields in a buffer gas environment, that you can at least cool them to a temperature which corresponds to something like maybe thermal energies. And then you can have a bunched extraction, and then you can do a detection here gated on the arrival time of your bunch. And this is illustrated here in these two spectra. So the upper spectrum would be the detection of the fluorescence without applying your gate. You can barely see any structure at all. And if you now gate on the ion bunch, you see a very nice spectrum of different spectral lines. As I said, this technique was introduced in 2002 in Uvascular, and you find some more details in this reference given here. So this has really improved the sensitivity of collinear laser spectroscopy significantly. However, we still typically need a yield on the order of 10 to 3 to 10 to 4 particles per second, which is sometimes just impossible to get. This has led to another approach, and the approach is called resonant ionization laser spectroscopy. So in this case, we use more than one laser, so at least 2, sometimes even 3 photons. We do an excitation from an atomic ground state by one transition to a known excited state. This would be the corresponding cross-section for the photon absorption. This is rather high. And then we need to use a second excitation step to bring the atom into the continuum, and so that is to ionize it. And there are 2 or 3, let's say 3 most commonly used ways. The one is the brute force approach, where you have a non-resonant transition. This has, of course, the lowest cross-section, but you can partly compensate by using very high power. You can have an excitation to so-called auto-ionizing resonances, which are sort of bound states in the continuum, which would then immediately decay. If these exist, they can be quite efficient, but you will not have them for all cases. Or what is very often done, you can excite high-lying Rydberg states. This is again relatively efficient. And then you can have this remaining step either by field ionization or by collisions with, or by blackbody radiation. So there's various ways of getting this done. Now, why is this an advantage compared to the previous method that I mentioned? Well, the ion detection is usually more efficient than fluorescence photon detection. So you can detect an ion with close to 100% probability. And so that means if you convert your excitation pattern into an ion, you gain significantly in sensitivity. You must, again, have low background conditions, and this you can achieve in particular when you maybe detect your ion by the radioactive decay, or what is often, of course, used is you do a mass selective ion detection so that you suppress signals from other masses. This method is highly sensitive and is also used in ultra-trace analysis. And since the laser ionization is, of course, element selective, it is also quite frequently used in laser ion sources, and this has given a huge boost in a lot of experiments. And just very briefly, I want to mention that in recent years at ISOLDE, they have used a setup, the so-called CRIS beamline, where they combine the advantages of both systems. So a collinear spectroscopy, but then they do resonance ionization in a collinear geometry. And this is also meanwhile available, but I will not go into more details of this approach. Okay, after this quite long introduction, I will now go to where we are and what we can do. So this is a not entirely up-to-date image of what has been studied in laser spectroscopy. So everything which is shown here in color on the nuclear chart has been studied. There has been quite a lot of progress in recent years indeed, but I would want to make the point that, as you see, there are several regions which are not touched, and this is really largely limited by the production and the production scheme in particular. Traditionally, the work on laser spectroscopy has started on ISOLDE facilities because there you had low energy beams of good beam quality. So of course, pioneering work was done at ISOLDE or then at Uvescular or at other ISOLDE facilities around the world. However, at ISOLDE facilities, you cannot access refractory elements, you cannot access super heavy elements or transactinides, and so on and so forth. And so people have developed procedures to expand. So one of the first things that was added is the so-called IGISOL concept, which already includes a gas system, and recently additional variants of gas cells were used. The main idea is if you use different type of nuclear reactions like fusion evaporation reactions or maybe charged particle induced fission or projectile fragmentation, you very often have to deal with high energy reaction products, where high energy means relative to the energy scale you want for your atom. And then you need to slow down the particles in a very simple and efficient way. And this is usually done with the help of buffer gas systems. And this has really expanded the access that we can do. So in the meantime, we have a couple of regions that became available, and I will try to discuss some of them today. So of course, we want to study refractory elements, and some of them are the ones here in the region between calcium and nickel, where calcium, of course, is a very well-studied isotopic chain, but many elements in between had not been accessible. The tin isotopic chain and somehow the vicinity is quite interesting because it is one of the longest isotopic chain that we have available. It involves two doubly magic nuclei, tin 100 and tin 132. So there's quite a lot of interest in this region. I mean, there are other regions, for example, also here around n=40, when we know there are a lot of interesting collective effects. Another region that I will show you later on is the region in around N126, or for example, the lead isotopes, the bismuth isotopes, mercury. So this is again long isotopic chains, and as you will see, quite a lot of interesting effects. Yeah, and in recent years, we have started to push towards actinides, and hopefully in the near future, also transactinides will become accessible. So a few illustrative examples. I mean, there's of course a bit personal bias in here, and due to lack of time, I will really only try to give you a few examples. I have picked them. Well, the ISOLDE example I have chosen is of course partly this mercury case and the bismuth isotopes. This I have mainly chosen because I personally would think that if this observation back in the day in the mercury that I will show you in a moment had not been made, maybe this field would have not received the same push. I'll show you some nice work on silver isotopes from Uvescular, some of my own work on einsteinium and fermium, and if time allows, I'll also show you an example from the NSCL. Yeah, and there are of course many, many more results from various places around the world that I have no time to discuss today. Just a brief remark to these examples. So there is really the ISOL facility, classic, the IGISOL approach at Uvescular, and the other approaches involve fusion evaporation plus gas cell. ISOL is actually a mistake here, but it's not entirely a mistake because some offline studies have been made on einsteinium and fermium, so it fits. And yeah, fragmentation is used at Beckola at the NSCL at Michigan State University. Okay, let's get started and look into lead, bismuth, and mercury isotopes and the work that has been done at ISOLDE for many, many years. So this is the well-known ISOLDE facility. As you know, probably half of the protons used at CERN go to ISOLDE, not maybe to the LHC, but and the 1.4 GeV protons then hit the production target, and we have various hot cavity ion sources. Usually the atoms effuse out of the target and then they are ionized, nowadays very often by laser ionization. And then we have in principle two different mass separators, the general purpose and the high resolution separator, which would provide with different resolution mass separated beams. The important addition from recent years is the IS-cool radio frequency cooler buncher. And among the beam lines, you have here, for example, the CRIS beam line and the collapse beam line for laser spectroscopy work. So at ISOLDE, for example, you have added a lot of versatile equipment. So as I have said before, there has been quite comprehensive work performed over many years. I mean, one of the first results that really maybe sparked everything a little bit was obtained in 1972 on mercury. I will show you this result in a moment, but I wanted to briefly mention a few relevant improvements on the detection and preparation side. Of course, there has been a lot of work done on the laser system for the laser ion source. There has been some developments on the different type of ion sources also, but I will not go into the details. But I wanted to mention the addition here on the detection side. Of course, one thing that has been used quite often is the windmill, more or less introduced by the Löwen colleagues, where you have the possibility to detect radioactive decays. But in recent years, the multi-reflection time of flight mass spectrometer has been very beneficial because a lot of the experiments are actually limited by isobaric background. And with the mass resolving power of such MR-TOF devices, you can indeed distinguish these isobars easily, and then you can use ion detection in this device, combine it with laser ionization, and do even in-source spectroscopy. Okay, so now let's look into some of the recent results. So I have picked here the mercury isotopic chain, which has been quite extended in recent years. Here's a couple of references to some of the work that has been published recently. So this is on the one hand side here, the neutron deficient isotopes, and nowadays one can go all the way down to 177 mercury. Of course, you can see that the intensities and the counts here are quite different. So on these most exotic cases, you already see these count rates are quite small, whereas for the other cases here, the count rates are already much higher. But nonetheless, with all the different detection techniques at hand, one can really cover the most neutron deficient mercury isotopes, and also important, the neutron rich ones, which are beyond or at the neutron shell closure at 126. There are also several things you see already in the optical spectra. Well, of course, you see that for the even cases, you have only one line, as you would expect, whereas for the odd cases, you get a splitting dependent on the nuclear spin, reflecting the hyperfine structure. But importantly, already now you see the change in the mean square charge radius, so the optical isotope shift. And if you now combine this, you get a figure which looks like this. So let's first look on the left side. So this would be the mean square charge radius delta R square as a function of neutron number. And you see here this huge change. So these first data points here, this was actually the initial work done in the 70s and 80s by the Otten group. Yeah? So they first had seen this dramatic change, whereas usually here in between you have a relatively smooth behavior. And then again, here you see the shell closure where you see a change in the slope, which is here amplified in this insert in comparison also between lead and mercury. Well, and of course, meanwhile, people relatively quickly came to the understanding that this huge odd even staggering that you see here reflects a change of the nuclear shape. So you say here, of course, near this shell closure, you have spherical nuclei, but you see that here in this region, in particular around neutron number 104, you have deformed shapes. And this is illustrated here. This is one of many theoretical calculations for potential energies in the mercury isotopes. I mean, for more details, I refer you to the publications given here as a reference. You can see that there are different minima which are relatively close in energy here between these different mercury isotopes. And you see even small changes, adding a few neutrons more or less, will really change the structure, or which of these minimums becomes more pronounced quite drastically. Of course, this has been studied in some more detail, but the main point is here you really have a sort of different shapes. So sometimes people refer to this as a shape staggering. And this is really one of the first measurements that was done, but it took really more than maybe 30 years until it was possible to extend these measurements to more neutron-rich cases. And here you see at these neutron numbers, in fact, this is already going back to a smooth trend. So this is quite interesting. So of course, there has been much more work performed at ISOLDE, also in many of the neighboring isotopic chains. And so you really start getting a more comprehensive overview and a more complete pictures. So what you often see here in between, in particular, of course, the lead chain here is a relatively simple case. You see very smooth behavior in between these neutron number 104 and the shell closure at 126. Yeah, as I said before, there is these kinks that you often see when you pass a shell closure. Of course, you know, here later on, there are additional effects like octopole deformation coming in. And here you see in the mercury case, this effect of the shape staggering. I will show you also similar things have been recently observed in business. And you see also in the gold isotopic chain, quite a few things are going on. Whereas, for example, in thallium, things are normally not so exciting, except maybe if you have isomeric states. But you see there's quite a rich information that you can obtain here. Yeah, and this is also studied extensively by theoretical model. I mean, here's, for example, some energy density functional methods with relativistic and non-relativistic approaches. More details are given here in this publication, but you can at least qualitatively see that this model C in particular, this functional here, is reproducing the data points not so badly. Yeah, and here you see relatively recent data that has been published in the beginning of the month, also from the ISOLDE collaborations extending the work to bismuth. And you see here in the first studied bismuth isotopes, you have a similar effect as you have observed it in mercury. And again, for more details, I would like to refer you to this physical review letter. But again, I can also mention here for the most neutron deficient case, you see that the count rates that have been handled were already quite low, but also you can see that this is beneficial, or not beneficial, is sort of thanks to the detection of radioactive decays. I mean, with ion counting, this would have been much harder. But so this is now a very nice tool set to learn more about these exotic nuclei. The next example I want to touch upon is the laser spectroscopy of silver isotopes. This is work from Uvascular. And this also involved a lot of technical developments. I mean, in fact, they say they needed almost 15 years of development to make these silver beams finally available. One of the technical things that were required is a so-called inductively heated hot cavity catcher laser ion source. So they really bring everything together. So this is the front end, where you have this ion source, sextupole ion guide, and then the extraction. And here you see the three-step laser excitation schemes. The laser are then brought into the ionization region, and then the ions that you produce by laser ionization are mass selected. But in this case, they did also need the full set of tools that they have available. I mean, here's one of these RFQ cooler buncher devices that I mentioned before, but they even had to use their penning trap system to learn about the structure and the states involved, as I will show you in a moment. So the work they did from the ion source side is more or less a follow-up of some work that had been initiated at GSI many years ago by Reinhard Kirchner. And he had found that excellent extraction of silver is possible from graphite. And then together with the local ion source experts, they had prepared this new ion source, and more details are given in this publication. And so what they can achieve now in combination with the panning trap. So here you see a detection of ions after in the panning trap. They even have selected the state. I will not go into detail how this is done, but they are using a phase imaging method that we have developed at GSI a few years ago. And this has such a high mass resolving power that you can distinguish between the ground state and the isomer, in this case silver 99, where you have a 9½ plus and a 1½ minus isomer. And you see these are different counts in these blue gates. This can be used to count which state has been excited, and then you can vary the laser frequency, and then of course you can get the frequency spectrum. You can also obtain isomeric yield ratios, and if you do so, you see here that is what they call trap-assisted spectroscopy with a high laser selectivity. And here's one of the examples for this particular case. So this is now the laser detuning frequency and the corresponding counts. The blue curve here is the silver 99 case. The red data points show silver 96, so that is already relatively exotic. And you see here the on-resonant count rate was on the order of 1 ion every 5 minutes. So this is already very low. But at the same time, you see that there's a relatively low background due to these many selection steps that have been combined. Of course, as you can imagine, the future goal is to go towards silver 94 also, where there's this famous isomeric state where people want to know whether or not there is a 2-proton emission observed. Yeah, and then here you see some examples. There has been a publication for this, and yeah, and there's also been several theoretical calculations using energy density functionals, either the UniDev parametrization or the so-called Fayence functionals. And you see here, there is quite a good agreement between the data and the theory, but if you cross the n equals 50, you see an increase in the data, which not clearly is reproduced in any of the models yet. And so this is really something that is further being studied. It seems yeah, that in principle this Fayence functional reproduces these local variations a little bit better, but of course this needs to be studied in more detail. There's also more work in Uvascular on palladium isotopes that will soon be published. Okay, now I will move to the heavy elements and show you some work that we have recently performed on fermium isotopes. This is now really the upper end of the nuclear chart, and you see there is not so many isotopes that have been studied. I mean, we have added a few here, the ones in green very recently. This red data point had been performed by Hartmut Backe about 15 years ago, roughly speaking. And so one complication that I want to briefly mention, this is now atomic levels. So if you look into atomic levels in the actinides, you see that around Einsteinium, fermium, so green and orange are experimental data, blue are theoretical calculations, and you see as soon as we reach Einsteinium and so on, the data, of course, becomes much, much less, and there is, of course, no data yet for lawrencium and also not for Mendelevium. So this is an additional complication, so we need atomic theory to support this activity. The experiments have been performed at the GSI at SHIP. And so we have used this RADRIS method where we stop beams in the gas. This has been used for nobelium spectroscopy, which I will not discuss. This is happening in an environment of argon gas. The ion beam is stopped, accumulated on a filament and neutralized. A heating pulse evaporates the atoms again. They are ionized by 2 lasers. And then the ions are transported to a detector where the radioactive decay is registered. Now, there is a few tricks that you have to play if you want to measure fermium isotopes. Well, one trick that we have exploited is you can produce nobelium isotopes with relatively high rate meaning a few particles per second for 254, and then you let it alpha decay on the filament, and then you have access to the fermium isotopes 248, 249, and 250, or you go to electron capture decay branches and you go to 255 fermium. Of course, this has a very long half-life of like 3 hours. So we had to develop a new detector system to measure this really because of this long half-life. So this is not easy, but as I will show you in a moment, it can be done. And there are long-lived fermium isotopes that, 20 hours or 100 days. So 100 days is comparably long. 20 hours is already a little hard, but both can be produced at Oak Ridge National Lab in the high flux reactor, but only on a picogram level, which can be on the order of 10 to 6 to 10 to 7 atoms, but this is still sufficient to perform laser spectroscopy. So I will just show you what we have done in this case. And okay, yeah, so there you see the data that we took, where the upper panel shows the data at GSI. I should just highlight this case here, the fermium 254, because here one data point took about a measurement time of 8 hours, just to appreciate that this is very complicated. This is data that we took in Mainz in an offline measurement recently, and we are at the moment just measuring this again. We are also just studying this data again in Mainz. But what I wanted to show you here is that you already clearly see the isotope shift in this fermium isotope chain. And if you now convert this into charge radii, this is not yet with the fermium data because they are still being analyzed. I have also added additional actinides. So the red data points are the published data on nobelium. And the lines that you see are again calculations with energy density functional theory. A few of the references are given here, and you already see not too bad agreement. But of course, if you start looking into the details, there is an odd-even staggering. Once you cross this shell closure at 152, the question is, do you see a kink or not? So there are still quite a few open questions that we need to tackle, but this also requires additional data. Yeah, I will very, very briefly just flash this because I'm already a little bit late in my timing. I just wanted to briefly mention that also meanwhile, you can use laser spectroscopy on particles from projectile fragmentation. So at the NSCL or in the future at FRIP, they will produce fragments from beams at, let's say, 100 to 400 MeV per nucleon or something like that. And then they have a gas stopper in which these particles are slowed down, extracted as ions, and then in this Bekola Cooler buncher, they can provide it for collinear laser spectroscopy. And they have recently worked on nickel and iron isotopes. I just show you very briefly a result on checking the difference of mirror nuclei, iron 54 and nickel 54. So here you see the data for nickel 54. Here the data for nickel 60, of course, with much better statistics. For the nickel 54, the rate was something like 15 atoms per second. And so there's this is related to studying nuclear neutron skins and symmetry in charge radii between mirror nuclei. And so this can then also be compared to calculation or work that has been done, for example, in the Pyrex experiment at Jefferson Lab. And this has been studied in the context of the equation of state, which is relevant for the formation, for example, of neutron stars. And so you see that there's different results from different methods. So this is the work that has been performed here from the laser spectroscopy. But due to the lack of time, I would refer you to this publication here for more details. I will maybe skip this one here. And so before I come to my summary, I would like to briefly acknowledge people that have provided me with material. That is Ian Moore for the UFIL-trapped IGISOL group, Clemina Misono from NSCL, and Sebastian Reder from the GSI. So let me briefly summarize. So laser spectroscopy provides opportunities to obtain nuclear properties such as spins, electromagnetic moments, and changes in root mean square charge radii. This can meanwhile be done with very exotic nuclei. In this way, we can learn about the shape and the size of these nuclei. We can eventually also, I didn't show an example on this one, but we can learn something about nuclear configurations, for example, from magnetic moments. and we can identify isomeric states. A very important point to make is that technical and methodological developments have been crucial to make this progress. In particular, the use of the IGISOL device, of gas cells and of Cooler bunches have been very crucial to increase the reach towards more exotic and more rare nuclides. Nowadays, one can say we can essentially access all elements by the different nuclear reactions. And in the recent years, we have obtained many high-quality data sets. And with this, I would like to thank you very much for your attention.